Hello, welcome everybody to the Georgia Tech Graph Theory Seminar. Our speaker today is Theo Molla from University of South Florida, and he'll tell us about transversal CK factors and subgraphs of the balanced blowup of CK.
Yeah, thanks a lot. Thanks for the invitation to speak. So before I get started, I just want to say that everything I'm going to talk about today is joint work with Becca Ergim-Lidze, who's a postdoc here at the University of South Florida, where I am. Can you see the highlighter here?
Yes.
Okay, great. Okay, so let's get started. So what I'm going to be talking about is, as the title said, I'm looking at graphs that are like subgraphs of a blow up of CK, so a cycle with K vertices. So the n blow up here just means that each part has n vertices. And I'll always think of the parts as being V1 to Vk. So here we have maybe the blow up of a triangle. Here we have the blow up of maybe a 4 cycle. Okay, and see in the 4 cycle, the triangle, we have edges between every part. In the 4 cycle, we don't have edges between like these parts here, and the V1 and V3 and V2 and V4. So maybe a starting off point for this talk is this result of Magyar and Martin from 2002 that says that if n is large enough, so this is the k is equal to 3, so we're thinking about the blow up of a triangle. And so if n is large enough, and so the minimum degree of these bipartite subgraphs, so the bipartite subgraph induced by V1 and V2, that's the minimum degree is 2n over 3 plus 1. Here, also you have 2n over 3 plus 1, and here as well. For all 3 of them, if you have that minimum degree condition, then your graph is going to contain a collection of n vertex disjoint copies of a triangle. So think the parts here each are of size n, and we're having n vertex disjoint triangles. So we're essentially trying to cover the entire graph with triangles, disjoint triangles. And I'll call that in the future a triangle factor, is we covering the entire graph with triangles. So a generalization of this result then was conjectured by Fischer and Häggkvist independently. And so if you can notice that when k is 3, this is the same degree condition we have here for the Magyar and Martin result. And now we're thinking of subgraphs we're thinking about blowups of a larger cycle. So and as the cycle gets larger, this minimum degree condition is getting weaker. But what we're looking for now is maybe the n vertex disjoint now transversal copies of, say, so let's just talk about C4 for a second, of maybe like C4, if k is 4. Then we're thinking of copies of cycles that have 1 vertex in each one of these 4 parts. So we're not worried about cycles that have maybe 2 vertices in V2, 2 vertices in V3. Those aren't the kind of cycles I'm interested in. 4 cycles I'm interested in. I'm interested in 4 cycles that touch each one of the parts exactly once. And so so the conclusion is the same. So with this new degree condition, we're going to find n vertex disjoint now transversal copies of CK. And again, we're tiling the whole graph, so we call that maybe a transversal CK factor. And just one small piece of notation, instead of writing something like this out every time, I'm going to define now the minimum partial degree of my graph G. So we're always thinking of it as being the subgraph of some blowup of some other graph. And we denote that delta star of G, and that's just the smallest minimum degree over the bipartite subgraphs that correspond to the edges of the blowup. So like we're only considering that like between V1 and V2, V2 and V3, V3 and V4, and V4 and V1. We're not considering here and here because there are no edges there between V1 and V4, and between V1 and V3 and V2 and V4. Okay, so yeah, and what I want to say is, I'll say it right now, is that the main result is that we were able to show that this conjecture holds asymptotically. And we'll get to that in a second. So first, let me just quickly go through the sharpness examples for just the triangle case. And the idea is you've got your three parts, V1, V2, and V3, and then you're taking each part and then dividing each part now into three parts, each of equal size. So I call them UI, WI, and ZI. And what do you do? So you place edges something like this, where this blue edge is representing all of the edges from that are possible between U1 and W2. So there's a complete bipartite graph between those two parts, and a complete bipartite graph here, and between these two parts here and here as well. And the key point is that there are no triangles here. Okay, so, and then to complete the construction, we add from Z here, all of the vertices in Z are adjacent to everything in U2, W2, U3, W3. That's what these red lines here are meant to represent. And same thing with Z2. Z2 is adjacent to every vertex in Z2 is adjacent to all of the vertices in U1, W1, and all of the vertices in U3, W3. And you can see that this graph is actually, it's every vertex has exactly 2n/3 neighbors in the other parts, in the other two parts. Like for example, this vertex, he's adjacent to everything here and everything here. Okay, that's 2n/3. And maybe this vertex, and maybe here, he's adjacent to every vertex here and every vertex here, and also every vertex in Z3 and every vertex in W3. So yeah, in every one of the other two parts, he has 2n/3 neighbors. So we have this 2n/3. We have minimum partial degree 2n/3, and one thing is there actually is a there would be a C3 factor in such a graph, but you can modify it slightly so that it doesn't have a C3 factor. So how would you do that? Well, one thing to note is that this, if I take the union of Z1, Z2, and Z3, then I have a triangle cover. And what I mean by that is that every single triangle has at least one vertex in Z. So think about what would happen if somehow Z was now made smaller than N. So right now it's exactly N, but maybe if I decrease the size of Z3 by 1, then my minimum degree might drop to 2n/3 minus 1, but I would no longer have a C3 factor. Because recall, we're trying to get n vertex disjoint triangles, and every single one of them has a vertex in Z, so there's no way I can do it if Z is somehow less than n. There aren't enough vertices in Z to get this C3 factor. I mean, another way to do it, it's somewhat similar, is to notice that Z1, Z2, and Z3 is actually an independent set. There are no edges here. And if I somehow increase the size of Z now so that so I have an independent set of size that's larger than Z, so maybe by increasing Z3 by one vertex and decreasing W3 by one vertex, I now don't have a C3 factor. I mean, you can think about, you can see this by thinking, okay, well, I'm trying to cover every single vertex in my graph with disjoint triangles, but now no triangle can have more than one vertex in Z because Z is an independent set. Okay, so there's no possible way of covering Z, so there's no possible way of covering the entire graph. Okay, there's one more thing we can do here, and this is where the +1 comes from. So what happens if you have a picture like this? Well, we've changed what's going on here with the edges here, where instead of having that kind of crisscrossing edges, we now have just these two disjoint blow-ups of triangles. And this part hasn't changed, but it's still true that this is an independent set here. So if there were to be a C3 factor of this graph, then it would have to be that every vertex has exactly one vertex, exactly one vertex in Z. Every vertex in my C3 factor would have exactly one vertex in Z, which means that every triangle in my factor would have exactly two vertices outside of Z. And that would mean that there would be a perfect matching of this part of the graph, which I cannot have if n over 3 happens to be odd. So I'm assuming here that 3 divides n just for convenience. But if n over 3 happens to be odd, then I certainly can't have a perfect matching of the U1 union U2 union U3 because I'd have an odd number of vertices there. And I wouldn't have a perfect matching of W1, W2, W3 either. Okay, so there's no perfect matching of this part of the graph. Okay, so that's what happens. And this graph has exactly 2n, the minimum partial degree is 2n over 3. So you actually need this plus 1 in order to force a C3 factor. And I just want to make one more point about this graph here, which I'll call gamma n3. It's that gamma n3 has a fractional C3 factor, even in the case when n over 3 is odd. It doesn't have a regular C3 factor, but it has a fractional C3 factor. So maybe I'll quickly say, like, a fractional C3 factor, one way to think about it is it's like you can formulate this problem of finding a C3 factor as an integer programming problem. And then this would kind of be the relaxation of that problem, would be looking for a fractional C3 factor. Another way of thinking about it maybe quickly is like if you have a fractional C3 factor would be something like where you assign a weight to the triangles in your graph, the C3s in your graph, and positive weight to these to all the triangles in your graph. And the rule is that at any vertex, if you sum up the weights on all of the triangles that include that vertex, you cannot exceed 1. So, and then if you follow that rule and then you sum up all the weights on all the triangles and it sums up to exactly n, then that would be a C3 factor, a fractional C3 factor. So this one, it's not hard to see that it has a fractional C3 factor, but it doesn't have an actual C3 factor. The other ones didn't have a fractional C3 factor or a regular C3 factor. Okay. So let me talk a little bit about the history of this. In 2000, Johannson proved that this 2n over 3 condition holds asymptotically. 2n over 3 plus the square root of n gives you a C3 factor. And here I'll say, so Magyar and Martin actually proved something quite a bit stronger than what I said earlier. They said that, okay, if your partial degree is at least 2n over 3, then you're going to have a C3 factor unless you're exactly this graph, this gamma n3 that I was describing on the previous slide. That's the only thing that can stop you from having a C3 factor when you meet this minimum partial degree condition. Okay, and what's normally known as Fischer's conjecture then is a generalization of this result, which we're generalizing it when we're thinking of like maybe the C3 as being a complete graph on 3 vertices. So now we're looking of like complete graph factors. This can also be seen as like a generalization of the Heinel-Zemretti theorem. And so this had quite a bit of interest, and it was proved. So for k equals 4 by Martin and Zemretti back in 2008, and then asymptotically for k greater than or equal to 5, that was proved by Low and Markstrom and Keevash and Mycroft simultaneously and independently. The publishing dates were different, but those were really done at the same time. And then for large n and all k greater than or equal to 5, it was finally resolved by Keevash and Mycroft. And their result is actually similar to this, where there is, so the way this is stated is, and the way Fischer initially stated it is not quite true. It's missing the +1 here in this special graph, but and there's a generalization of this that shows up, but and Keevash and Mycroft actually proved that is the only possible exception to this conjecture being true. Okay, so now here are the results again. The Johannson result and the Magyar and Martin result. So the generalization where you think about the C3 as being a cycle instead of a complete graph is what I was showing on the first slide. Is this this conjecture of Häggkvist and Fischer they conjectured it independently, and so this is what we proved. We proved that okay, so 3 is already taken care of but for the k greater than or equal to 4 case, we showed that, yes, asymptotically, this condition here is the correct condition for a transversal CK factor. Okay, and quickly I'll say like a little bit about the sharpness here. It's very, very similar to what we saw earlier. So here I'll just do the k equals 4 case. And we do something similar in the picture here, where these blue lines again represent complete bipartite graphs. And in this part of the graph, we have no transversal C4s. That's the point. And here we're attaching the Z in a similar way to what we did before, but okay, now the Z1, he's not adjacent to anything in V3, so he's just adjacent to U2, W2, and U4, W4. Again, because we're thinking of this as the blowup of a C4, so there's no edges between V1 and V3, and no edges between V2 and V4. And so we attach edges in this way, and now that the Zi's are size n over k, and then we split up the remaining part of each part exactly in half. And one half will be the U1, UI, and the other half will be WI. And so the logic here is, why are we getting a sharpness example? Well, so as I said, there are no transversal C4s here, or CKs when you generalize this to a larger cycles. And so this, if I union all the Z parts, I get a transversal CK cover. And again, if this transversal CK cover is somehow less than n, there's no way I can get a CK factor, a transversal CK factor, because there's just not enough vertices here to get n vertex disjoint CKs. Okay, and you can compute that, okay, yeah, this actually comes out to be the right minimum degree. So maybe I can decrease it slightly by maybe making Z4 one vertex smaller and making W4 like one vertex larger. Your minimum degree will go down by one, your minimum partial degree will go down by 1, but then you will have no CK factor. Okay, so now let me try and spend a little time talking about the proof of this result. So here is what we're trying to prove. And the first thing I want to say is that the absorbing method works for this problem. So it's a very straightforward application of the absorbing method of Rodel, Rudzinski, and Zemretti. It turns out, luckily, that it works without much, without much work. You just follow the basic procedure and it will work. And what does that give us? That means that you don't really have to get this. You're not really looking for a transversal CK factor. You're looking to just, you don't need, because you don't need to cover the entire graph with transversal CKs. You really only have to prove that, okay, for any sigma greater than 0, if you make n big enough, then you can tile all of the graph except sigma times n. Well, you can find, you would want to find n of them, but all you really need to find is n minus sigma times n of them. So you're missing sigma times n of them. The rest of them will be absorbed by this method of Rodel, Rudzinski, and Zemretti. So that makes the problem much easier to do. And so let me tell you the approach. So now that's all we need to prove is this. So let's just define m to be then sigma times n divided by k. So I'll assume that n is such that, and sigma are such that this turns out to be an integer. It really doesn't matter. You've got some wiggle room with the absorbing method, so like losing one or two or a few transversal CKs doesn't matter at all. But for simplicity, let's just assume everything divides. And as well, we'll assume that this comes out to be an integer, n divided by mk. And I just write here that it's 1 over sigma to say that, okay, this t plus 1 is just some constant depending on the sigma we're given. And we can make n as large as we want to. So n essentially goes to infinity. and this t is some fixed constant. Okay, so the idea now is we're going to have t steps. So some fixed constant number of steps. Maybe it's a lot, right? Sigma could be quite small, but we're going to have a lot of, but a constant number of steps, many steps, but a constant number of them. Okay, and what are we going to do? We're going to find, in each step, we're going to find mk, a tiling of size mk. So we're going to find mk vertex disjoint ck's. And these won't overlap with the ones we found in previous steps. So in the end, how many will I have? I'll have t times mk vertex disjoint ck's. And okay, but t plus 1 times mk was n. So I'm only missing mk of them. So it works out to be n minus sigma times n. So, and the rest will then be absorbed. Okay, so how do we do this? So again, this is the plan. We're going to construct t disjoint tilings, each of size mk, and we'll do this iteratively. So the first step is we uniformly at random, for each one of the, we partition each one of the parts into t plus 1 parts, now each of size mk. So we do this uniformly at random. And with high probability, what will hold? Well, the only thing we really care about is that every vertex is going to see have the right proportion of its neighbors inside each part. And this will hold. So for example, like a vertex in W2, in V2, take any vertex in V2, and then look at some part in V1, maybe W12. For example, yes, wherever it was here, look here. He should have the right proportion of neighbors inside, of his neighbors should be in there. His neighbors in V1 should be in this part. So the whole thing was size n, and now it's mk, so it should be, he should have about this number of neighbors times mk over 2 inside each part. And maybe this constant, this epsilon, you can knock it down maybe by half. So it's 1 plus 1 over k plus epsilon over 2 times mk over 2. That's how many neighbors a vertex in V2 will have here. And that's how many vertex of V4 will, any vertex in V4 will have into any one of the parts. So this holds for every single vertex in the graph and for every single part we've made with high probability. So, okay, we just have to make n large enough for this to work. So what are we going to do? So on step T, we're going to find a tiling of size mk. And where are we going to find it? We're going to find it in UT union WT. And what is WT? Well, WT is kind of easy to explain. WT is just a column here. So this would be W1 is this column. W2 is this column. And hopefully I've got everything in the correct order, where this is W1, this is W2, this is W3, and this is W4. And what is UT? Well, UT is the union of this. Well, what is this? So this is the uncovered vertices in like the previous columns. So maybe if we're on, like if T is 3, then UT would be the unused vertices in the previous 3 columns. So let's think about this for a second. So let's actually start with just T is equal to 1. That's our first step 1. On step 1, what's WT? W1 is this column. What's U1? U1 is this column, because no vertex is covered yet. I haven't found any triangles yet, or no, I haven't found any cycles yet, any C4s. So this looks like k is equal to 4. So I haven't found any C4s yet. So U1 is this column and W1 is this column. And the thing we're going to do is now we're going to find we've got, so 2mk vertices here, 2mk vertices here, 2mk vertices here, and 2mk vertices here. Everything here, we will not totally leave that untouched in this first step. So everything here is untouched in the first step. And in here, we're going to find, I mean, if I wanted to cover everything here, I'd have to find 2 MK transversal C4s. But I'm just going to cover half of it. I'm going to cover half of it. I'm going to just find MK C4s. Okay, so let's say I could do that. Then what would be left here? What would be left here is MK vertices in each part, because I only covered half of this. And then I would be in a similar situation. I'd have MK vertices here that are uncovered in like these first 2 columns. I'd have MK vertices in each part. And then I would use one of these previously untouched columns to then try and get another MK cycles. And then I would do it again. I would have MK MK uncovered vertices here. And then I would use one of these untouched columns to try and extend the tiling that I've done so far. Okay, and I keep doing that all the way until I get to the end. And then in the end, it should be that I just have MK vertices left uncovered in each one of these parts, which is what we wanted to show. We would have constructed T disjoint tilings each of size MK. So in this case, T is equal to 8, right? And I have 9 columns here. Okay, so the thing I didn't tell you was how we're doing this, how we're doing a single step. So let me try and explain how a single step works now. So these are the uncovered vertices. This is UT from the previous slide. And this is an untouched column here, WT. And here are some assumptions I have going in. I assume that, okay, so let's see what's going on here. So for every vertex, so these are the relevant vertices for like the ith part, the ones above it and the ones below it. Those are the only ones that are going to have, those are the only vertices that are going to have any neighbors into the part VI, right? But for every single one of those relevant vertices, I'm going to have a little bit more than half of my neighborhood inside each one of these parts will be a little bit more than half, right? This 1 plus epsilon over 2 times MK over 2. So MK over 2 is half. Yeah, I didn't say, remember that each one of these has MK vertices. Each part as it intersects UT. And likewise here we have MK vertices in each one in WT as it intersects each one of the parts. Each one has MK vertices. So all of the all of the vertices that are relevant will have a little bit more than half. It will be adjacent to a little bit more than half of the vertices here. Okay, and here for the untouched stuff, things are still very, very good, right? Because I have this original degree condition. Well, it's only gone down a little bit. So this comes from being this random partitioning. Okay, so those are my assumptions going in. Can I now find MK vertex disjoint transversal CKs? Well, I do another random partitioning now of the uncovered part. I split it up into K parts. So this was size MK before. Now each one of these parts will be of size exactly M. Each one of these smaller parts are now of size exactly M. And again, it's a random partition. So I didn't mention the Chernoff bound, but yeah, this is a consequence of the Chernoff bound that, okay, since I had this degree before, I should have the right proportion of neighbors inside each one of these now smaller parts, which means I should see a little bit more than half of the neighbors in here. So, and that should hold for everything in the other 2 relevant parts. Now, what does that imply? Well, one implication of that is that between here and here, it's like a bipartite graph, and the minimum degree is, about half of the, so it's like a balanced bipartite graph of size m with parts of size m, where the minimum degree is at least m over 2, right? That's what's happening here. So that means that there's a perfect matching between just in here. And likewise, there's a perfect matching right here, because this will also be a balanced bipartite graph with parts of size m, and the minimum degree will be m over 2, at least. So here's what I get when I put in these perfect matchings. So that's starting to look like a transversal C4. What I need to do is I need to kind of complete this by finding a common neighbor of this vertex and this vertex in here maybe. So this would be a likely place to look because my degree into this part of the graph is good. So what is the common neighborhood? How big is the common neighborhood of this vertex and this vertex into this part right here? Well, let me see. I would have to multiply this by 2 to get a lower bound. I'd multiply it by 2 and then subtract the whole size, which is mk. So if you look at that, you would see, okay, well, that looks like it's about m. It's actually a little bit larger than m. So that means the common neighborhood of these two endpoints is about m. So I can find one, just greedily find one in the common neighborhood. The common neighborhood of these two here is m as well. So I can greedily actually find a common neighbor, a disjoint common neighbors, distinct common neighbors for each one of these. Well, these will be m. So remember, these parts are just size m. So, and the common neighborhood here was m. So we can greedily just complete these into transversal C4s in this case. And now I can do something similar here, except now this was left untouched, but now I'll leave this untouched, and I'll do something like this, find a perfect matching between in this bipartite graph and then a perfect matching in this bipartite graph, and then complete them into C4s by just greedily selecting things out of the common neighborhood. So something like that. And I keep doing that until I've got what I wanted. So, okay, great. I was able to, if I make these assumptions, I'm actually able to find MK vertex disjoint CKs, which is what I wanted to do. But we want to be able to go into the next phase of the algorithm, of the process. So that means I want this to hold, but for the next round. So in the next round, what will the uncovered vertices be? The uncovered vertices will be the black vertices here. And what will my degree be into those black vertices? So yeah, so this is in the next round, the UT plus 1, in other words, will be the black vertices here. That's exactly what UT plus 1 is going to be. And then I'll have a new, totally untouched column that will be the WT plus 1. Okay, so what is the degree? So let's see. Well, into this part, it was about half. So it's at least m over 2. That comes from the random partitioning. And then when I started, I had this many neighbors up here. But I've lost, maybe these were my neighbors, right? So I've lost at most m neighbors. So what's my degree? Well, it actually works out to be exactly what we want it to be for the next round of the algorithm. Okay, so that in that way, we can kind of, I'll go back quick. We can kind of go through, that's exactly what we're doing in each one of these steps. So when we start off, we definitely meet the conditions because it's actually much larger than we need. But then after that, we meet the conditions by the argument we just went through. And we're just doing that again and again, t times until we've covered most of the graph. And then what do we do at the end? Well, that's where absorbing comes in to get these final MK, these remaining vertices, this small set of remaining vertices. Okay, so maybe okay, so let's see how much time. I've got I've still got some time. So let's there's more to this, more to say. I have more to say. I mean, I maybe that could be a stopping point, but there's actually some more things that we thought about. So here are here's what we proved, but we realized that maybe we can relax this in some way, right? We can relax this by saying, okay, well, does it really have to be that every single one of these relevant bipartite graphs has to have this minimum degree condition? Could they somehow like vary in size? So that's this conjecture down here. That's what this conjecture is about. It's saying that it doesn't have to be that every single one of them sees, has this kind of a minimum degree. It could really be that this is essentially what it's saying is that the average has to be what's up here. The average minimum degree has to meet what's here. And okay, so where is this n over 2 coming from? They all have to be bounded below by n over 2, all of these minimum degrees. Because it's not too hard to see that if you actually had a CK factor, you'd get a perfect matching between, that would imply a perfect matching between every single, so like between Vi and Vi plus 1, right, for I going from 1 to k. So if your minimum degree was somehow less than n over 2, then you would no longer be guaranteed to even have a perfect matching between those two parts. So you definitely need this condition here. And then besides that, we're saying, okay, but besides that, your minimum degrees can vary. Okay, so that's our conjecture. We don't know if that's true or not. But we have some evidence that might back it up a little bit. So first of all, okay, so the main result that I was talking about before is exactly this conjecture in like the uniform case when they're all the same. That's just exactly what the conjecture is. Or that's exactly what our result says. Okay, but this is a totally different result, is we actually proved that this holds when k is equal to 3. You can do the triangle factors when you allow the minimum degrees to vary. So, and we'll talk a little bit more about that in a second. And also, so this one implies something. It's not too hard to see that this conjecture actually holds when all but at most 3 of these minimum degree conditions are very small, right? So this is like the case where most of them are small and only a few of them are large, right? Only at most 3 of them are big, these minimum degree constraints here, right? Only 3 are big, the rest are small. That's one way to think about it. And maybe I'll say quickly, why do we have this? This is just a corollary of what we proved here. Well, think about the k equals 4 case. So we have, these are our minimum degrees now, delta 1, delta 2, delta 3, and delta 4. And this is the average is what we want. So this is what the average should be. And let's say that delta 4 only was very, very small. It was the smallest it could be was n over 2, but maybe it's just a little bit more than n over 2. So one thing we have is that there has to be a perfect matching between V1 and V4. So so I didn't say it before, we've used this fact before, that your minimum degree, if you have so here we have a balanced bipartite graph with parts of size n, and the minimum degree is n over 2, you get a perfect matching. Well, that follows from Hall's theorem, or you can prove it without using Hall's theorem. It's not hard to prove, but it definitely follows. So you get this perfect matching here from V1 and V4, and now all you need to do is contract the edges of conditions, delta 2 will be the other, and then we got rid of this one. The last one will be delta 3, right? Because we've contracted V1 and V4 have been kind of joined together into one. So this delta 4 condition goes away. But now it's, if you do this computation, you'll see that, oh, well, but delta 1 and delta 2 and delta 3 have the right average minimum degree to for the k equals 3 case. So we've reduced it from the k case to the k minus 1 case. So you could do this if you had, like, if k was something larger, like 10, you could keep doing this for all the small ones, all the small minimum degree conditions, if there were only 3 large ones, and then you'd have only 3 left, and then you could apply our result. Okay. So that's some of the supporting evidence we have for the conjecture. Again, we don't know if it's true or not. So here's our result, where we prove that, okay, for just the triangle case now, you only need the averages to be 2/3 plus epsilon times n. They have to be at least n over 2, but you need the averages to be the average should be 2n over 3 plus epsilon times n, instead of each one being 2/3 times n. We just need the average. Okay, but even this, so this is tight. I mean, this is a nice result, but and potentially you could stop here, but there's still something that's a little bit strange that we don't really totally understand, because the issue is we don't know if you just change this whole theorem and replace this condition here, the average of them being 2/3 plus epsilon times n. Well, what if you just change it so that the largest two, the average of those has to be 2/3 plus epsilon times n? We don't know if that's good enough to guarantee a triangle factor. So, like, we don't know. So maybe one of the most interesting cases of this would be, like, if you remember back the Magyar and Martin result, that was requiring all 3 of those minimum degrees to be 2n over 3. But we actually don't know if maybe one of them can be much smaller. Maybe one of the minimum degree conditions only needs to be n over 2. And then you can still find a triangle factor. That seems kind of strange to me. I'm not sure if it's true or not. We're not ready to make any kind of conjecture in that way, but we weren't able to find an example that shows that this isn't just enough to get you a triangle factor. And even more than that, we were able to show, okay, so with a little more work, you can even make the absorbing method work in this context. And maybe, okay, so the lower bound, we had to fudge a little bit on the lower bound as well. But when you do that, absorbing does work. Okay, and yeah, maybe, okay, it doesn't matter. So it's kind of trivial to show that. So what are we thinking right now? We're thinking, okay, we want to find a counterexample to this kind of condition, something that some blow up of a C3 that meets these minimum degree conditions but does not have a triangle factor. So this is the strange one where we've dropped this third one down to n over 2. And what would be the normal way you try and do that? Okay, well, try and find an example where the independence number is greater than n. Could you find something like that with these conditions? Well, it's kind of trivial to show that you can't. The independence number still must be at most n. And then another thing you might try and do is try and find a triangle cover that has size smaller than n. If you remember before, that immediately implies that you don't have a triangle factor. And we weren't able to do that either. Actually, we were able to prove that you can't do that. That the triangle cover number, so we'll get to that in a second. But let's first see this kind of trivial fact about the independence number. So what's going on here? Okay, we have our minimum degree condition. The largest two are of size at least, the average of the largest two minimum degree conditions is 2n over 3. And so what does that imply? If I look at 2 times the first one plus the second one, that's certainly bigger than 3/2 times the first one plus 3/2 times the second one, because the first one is bigger than or equal to the second one. So delta 1 is bigger than or equal to delta 2. And then this is telling me, what if I multiply both sides by 3? It's telling me that this is at most 2n. So actually, for this one, this is the this is the condition you need. 2 delta 1 plus delta 2 is greater than or equal to n. So you definitely always need that. For sure, you need 2 delta 1 plus delta 2 is greater than or equal to 2n. But let's see. So so you could let Z be an independent set. So any independent set in this graph, and we'll let Z be, well, little z be the whole size, and Zi is just going to be the size of its intersection with the ith part. And so, of course, Z is equal to the sum of Z1 plus Z2 plus Z3. Okay, so obviously Z can't, if Z is contained in one part, then your independent, the size of Z is less than or equal to n because each part has size n. Okay, remember, we're trying to show that under these conditions, you can't have a large independent set, an independent set that's larger than n, which would imply that you couldn't have a C3 factor. Okay, so what about if you hit just 2 of the parts and instead of all 3 parts? So that's what I'm trying to write here. You hit Z, you miss Zi, but you hit the other 2. Well, then how big is Z? Well, it's definitely Zj plus Zk because you missed Zi. But how big are those? Well, maybe think about J being 2 and K being 3. So, or maybe even better, think about J being 1 and K being 3. What's going on? Well, I've got a vertex in my independent set there's a vertex from my independent set in V1 then. And there's a vertex from my independent set in V2. So all of the neighbors of that vertex are not in the independent set. So if I look at the neighborhood here, it's giving me some kind of an upper bound on the size of Z1. So like you could think maybe Zj has to be less than or equal to the minimum degree between these 2 parts, n minus the minimum degree. And the same thing applies in the other direction. So yeah, there's a vertex here from my independent set. Or no, maybe I did it backwards. So there's a vertex in this part that's in my independent set. If I look, all of his neighbors are not in the independent set. So the size of then maybe Zk is n minus the minimum degree between these 2 parts. So I add that all up, and why is it less than or equal to n? Well, that's just because the minimum degree is at least n over 2. Okay, and then you're doing something similar if you intersect each one of if the independent set intersects each one of the parts. Because then you can think, okay, well, how big could Z1 be? Well, I look at a vertex here that's in my independent set. I look at his neighborhood. It's delta 1. So that means that Z1 has to be less than or equal to n minus delta 1. If I look at a vertex here that's in my independent set, all of his neighbors are not in the independent set. So that means Z2 is also less than or equal to n minus delta 1 because the minimum degree between these parts is delta 1. And then Z3, I can say, okay, well, Z3, I look here. Here's a vertex in my independent set. He's got delta 2 neighbors into V3. So that means the Z into V3. So that means that the size of Z3 is less than or equal to n minus delta 2. I just add all of those up, and I use this fact here, and I get that Z is less than or equal to n. So yeah, that's kind of a simple argument to show, yeah, you can't have a super large independent set in this setting. And then for the triangle cover, it was actually not easy to prove at all, for us anyway, that that you can't have a triangle cover. Like every triangle cover has to be yeah, has size at least n, right? Sorry, I'm getting tired now. So every triangle cover has size at least n in this case, in this setting. So here's the setting we're in, and every triangle cover needs to have size at least n, so bigger than or equal to n. Okay, so yeah, so one more. Let me just. Okay, I probably now I actually never asked how much time I had. I think I've gone over time, but let me just say something real quick. Now we're interested in the range where delta 1 is between 2n over 3 to 5n over 6, because, okay, well, definitely we don't want delta 1. Delta 1 is the largest. It can't be less than 2n over 3 because I want the average to be 2n over 3. And when delta 1 gets all the way up to 5n over 6, then you need like delta 2 to be n over 2, right? And so this isn't actually playing a role anymore at that point, right? Because you get it just from here. So this is really where we're interested in this range between when delta 1 is between 2n over 3 and 5n over 6. Okay, and what we have are, well, certainly there's an example when delta 1 is 2n over 3, and we have examples that when delta 1 is between 3n over 4 and 7n over 9, where this condition, so this is, if you think about this condition here, it's really saying that delta 2 has to be larger than or equal to 4n over 3 minus delta 1. So only in these, the point is, only in these ranges do we even know that this is necessary. Outside of this range, if you're in here but you're not in this range, perhaps even like a weaker condition on delta 2 might be necessary. I mean, we don't know. We just don't have examples. And I won't get into the example too much here because I feel like I've taken enough time. But it's basically like the examples we saw before, the original example, except instead of splitting it into 2 parts, you split it into 3 parts. And still this part is supposed to be triangle free. But we've got something, see, things are very unbalanced here now. Here, like this one is adjacent to these 2 parts, and this one is adjacent to these 2 parts. This one is adjacent to these other 2 parts here. And here it looks very similar to what we had before. But we're trying to, like, the goal is to have delta 1 be larger, and then like the degree in delta 2 will be smaller. Anyway, this is the kind of examples we have for this range between 3n over 4 and 7n over 9. Anyway, I'll stop there. Yeah. So let's just say, let me just say one more thing. If you really did have a counterexample to this in this setting, right? What would be going on? You would know that your independence number would have to be n, and your triangle cover number would also be n, right? So those aren't stopping you from getting this C3 factor. Those 2 facts can't be the reason that you don't have a C3 factor. And you also have that absorbing works. So then it would have to be that G cannot have a fractional C3 cover. So if you had so if you're a counterexample and in this setting, then it would have to be that you don't have a fractional C3 factor because of, okay, so that's a well-known fact. And that would also mean that you would the fractional triangle cover number would have to be less than n, while the triangle cover number is exactly n. But anyway, so those would be some characteristics of a counterexample. Anyway, that's all I wanted to say. So thank you very much for listening. Yeah.
Thank you very much, Theo. Let us all thank the speaker. Are there any questions for the speaker? I have a quick question then.
Okay.
Are there similar conjectures for blowups of other types of graphs? So you mentioned the blowups of complete graphs and blowups of cycles, which was the main topic. Are there some kind of conjectures in greater generality for an arbitrary graph, maybe?
I don't know of any conjectures out there for anything else. I mean, that definitely is a natural thing to think about, but I don't know of them. Yeah, I'm not aware of anything.
Are there any other questions? Well, if there are no more questions, then let us thank the speaker again. And our speaker next week will be Taiza Martins from Fluminense Federal University.